Welcome to Theory of Computation. This is lecture number 22. We have started looking at complexity theory and we looked at deterministic Turing machines. What we did was we proved a very nice theorem on deterministic Turing machines. We said that if we have a Turing machine, a k-tape Turing machine, which runs in time tn, then we can find an equivalent one-tape Turing machine which runs in time t squared of n. So this theorem said that one can get rid of extra tapes and reduce the Turing machine to a single tape model at the cost of a quadratic penalty. Single tape Turing machines are different from multi-tape Turing machines, but this theorem shows that their differences cannot be arbitrarily large. It is bounded. You can always get rid of extra tapes at a quadratic blow-up in time. Therefore, if you have a polynomial time k-tape Turing machine, if you have a Turing machine that runs in polynomial time and uses k-tapes, you can always convert it to a one-tape Turing machine which runs in polynomial time. So for example, if you can prove that you can solve a problem in order n cubed time using, let's say, 12 tapes, then that would immediately imply that you can solve the problem in order n to the 6th time using one tape only. This is a very convenient theorem. After that, we started looking at non-deterministic Turing machines. Non-deterministic Turing machines are just like deterministic Turing machines, except when they take a step, instead of taking one step, they have several choices for taking the next step. So the computation of a non-deterministic Turing machine is like that of a tree. You can model the computation of non-deterministic Turing machine with a tree. This tree will have the initial configuration at the top, and at the first level, it would be all the possible moves that the Turing machine can make from the initial configuration. And at the next level, it would be all the possible moves that the machine can make from the first configuration, and so on and so forth. So you get a whole computation tree instead of a linear thing which you get when you follow the computation of a deterministic Turing machine. We said that we will define the definition of acceptance for a non-deterministic Turing machine was, since it's a computation tree, it has several branches, and some of the branches may accept the input and others may reject the input. So by definition, we will say that the machine accepts the input if there is at least one branch that accepts the input. So as long as there's one branch that accepts the input, we'll say that that X was accepted by a non-deterministic Turing machine. On the other hand, we will say that the machine rejects the input if all branches reject the input. And so, see, acceptance and rejection are not very symmetric when we are talking about non-deterministic Turing machines. Acceptance means that a string was accepted by one branch of the computation, and rejection means it was rejected by all branches of computation. This is imperative that you keep this definition in mind. You have to keep this definition in mind because if somebody gives you a problem and says, design a non-deterministic Turing machine to solve the problem, well, you will have to give them a Turing machine which will accept all inputs that are in the language and reject all inputs that are not in the language. And here acceptance means that you will design a Turing machine so that if you give it something in the language, there will be at least one branch in the computation that will accept that input. And if X is not in the language, then all branches will reject that input. So let's look at the overview of today's lecture. Today we will look at non-deterministic time and then compare it with deterministic time. After that, we will define a very important class of problems called P, and then we will define another very important class of problems called NP. So we will define what P is and we will define what NP is. One intuitive way to think about P and NP is, P is the set of all problems that we can solve practically. All problems that somehow we have practical algorithms to solve that problem. On the other hand, NP is in some sense a wish list, the problems we wish we could solve practically. It's just a little bit bigger than P. It is the problems that we wish we could solve in polynomial time. Well, we will be very formal with what these things exactly mean, but let's continue with the first theorem of the day. So the first theorem of the day will relate non-deterministic time with deterministic time. So we want to prove the following relation between deterministic time and non-deterministic time. Suppose t of n is a function where t of n is greater than or equal to n, then every tn time non-deterministic single-tape Turing machine has an equivalent 2 to the order tn time single-tape deterministic Turing machine. Thus, this theorem says that we can get rid of non-determinism at the cost of exponentiating the time. So if we are willing to pay that penalty, we can make every non-deterministic Turing machine into a deterministic one. Well, what is going to be the proof of this theorem? In the last lecture, we actually looked at an outline of the proof of this theorem. Today, we will follow it in a lot more detail. Basic idea is that if you take an input x and run a non-deterministic Turing machine on this input x, what you get is a computation tree. Well, what the deterministic Turing machine is going to do is find out what this tree is by painstakingly going through each and single node of this tree. Thus, if we want to know how long does this deterministic Turing machine take to simulate the non-deterministic Turing machine, we need to know how big this computation tree can be. Well, what we will do is we can examine the non-deterministic Turing machine, the transition function of this Turing machine, and find out what is the maximum number of choices that are allowed at any point. So we can find out what is the largest set. So delta maps Q, A to a set. We can find out the largest set and let's call it B. This means B is the branching factor of this non-deterministic Turing machine. If this machine is running, it cannot make more than B choices, or any node in this computation tree cannot have more than B children. We have one estimate which is on the branching factor of this tree. Another estimate we have is on the depth of this tree. We know that the Turing machine runs in time Tn, so that the depth of this tree is at most Tn. From this, we can actually get an estimate or an upper bound on how many nodes can be in this tree. Let's do that. This tree has depth T of n. B is the maximum number of legal choice given by n's transition function. Therefore, this tree can have at most B to the T of n leaves. In fact, if you see, the tree has B to the 0, that is one node as the root. On the first level, it can have at most B children. And on the second level, it can have at most B squared nodes. On the third level, it can have at most B cubed nodes, and so on and so forth. And on the kth level, of course, it can have at most B to the k nodes. So the total number of nodes in this tree is given by the geometric series 1 plus B squared plus B cubed, so on, all the way up to B to the T of n, which is the last level in this tree. If we sum up this geometric series, I hope all of you know how to sum up a geometric series, you will realize that this comes out to be less than or equal to 2 times B to the T of n. Every geometric series is bounded by its largest term, bounded by a constant times its largest term. So this tree has B to the T of n nodes. Well, so B to the T of n itself is just 2 to the order T of n. So that's how many nodes do we have in this tree. Now let's design a deterministic Turing machine that visits this tree. This can be done in several ways. Well, The book gives you one particular way, and here I will describe a slightly different way. They're not too different. Both of them are equally simple to understand. Let's look at them. Let's consider a string R over 1, 2, 3 up to B of length T of n. So let's say the string is 1, 2, 3, 1, 3, 4, 1, 2. This string will correspond to a computation of the non-deterministic Turing machine. This string is a computation of non-deterministic Turing machine on an input, and when the Turing machine has to make its first choice, this string is telling it what choice to make. So basically this string means that starting from the root, go to the first child in the computation tree, then go to the second child of the first child, and let's call that C2. Then look at the third string, it's 3, so that says from C2 go to the third child, and after that we have a 1, so it says that from C3 go to the first child of C3. Thus each string this way corresponds to a branch in the computation tree. And if I go through all possible strings, then I'm going through all possible branches in the computation tree. Now our deterministic Turing machine or deterministic algorithm is very simple. What it does is on input x of length n, it computes T of n, and for all strings s in R to the T of n, it simulates n. Well, it simulates n. How does it simulate n? Every time n has to make a move, it has several choices. It uses this string to make that particular choice. So the first time it runs across a choice, it goes to the first character of the string and sees which choice it is, and it takes that choice. Similarly, in the 78th step, when it has several choices, it goes to the 78th string of this string s, 78th character, and looks at the choice and makes that choice. So this is how it simulates this non-deterministic Turing machines. See, once the choices that are to be made by a non-deterministic Turing machine is fixed, it just becomes a deterministic Turing machine that if I tell you these are the choices that the non-deterministic Turing machines will make, then I'm telling you a branch in the computation tree. So this Turing machine simply works like this. And if any of these branches accept, it accepts. If it goes through all the strings, so it has gone through all the branches and none of them accept, then it rejects. The method that I have described to you assumes that we can compute T of n quickly. Actually, we can get rid of that assumption also by iterating over T of n. The details of that exercise are left to you as homework. Well, for each string, this simulation will take order T of n time. There are b to the T of n strings to simulate. Thus, the total time is T of n times b to the T of n, which is 2 to the order T of n. So we have a Turing machine which runs in time 2 to the order T of n. Well, there is a slight technicality that we have to deal with here. That technicality is, when I have described to you this Turing machine, deterministic Turing machine that simulates a non-deterministic one, to do the simulation, this Turing machine requires more than one tape. In fact, to describe this Turing machine, if you do it in detail, I gave you a high-level description. If you go to the implementation level description, you will realize that you need more than one tape. Now what we will do is we'll apply our previous theorem. And that says we can get rid of the rest of the tapes if we are willing to pay a quadratic penalty in time. So let's do that and compute and see what is the total time taken by this deterministic Turing machine. If we convert this multi-tape Turing machine using the previous theorem, the total time taken will be 2 to the order T of n whole squared, which is 2 times order T of n, and which is 2 to the order T of n because 2 is a constant, and when you multiply it with order T of n, you can ignore it. And hence our theorem is proved, so we can get rid of non-determinism at an exponential cost in time. Now, let us move on to the next thing. What we want to do now is to decide an extremely important class of problems called P. We want to know which problems can be solved in practice. Thus, we define the class P as follows. P is the union over all k of time n to the k, or more elaborately written as P is time n union time n squared union time n cubed union time n to the 4. So, P is the set of all problems that can be solved in time n to the k, order n to the k, using a single tape Turing machine. Well, if you think about it, I could have also said P is the set of all problems that can be solved in time n to the k using a two-tape Turing machine. That's because of our previous theorem. See, if a problem can be solved in time n to the k by a multi-tape Turing machine, then it can be solved in time n to the 2k by a single tape Turing machine. So the definition of P is invariant under how many tapes you allow in your model. That's a very nice feature of P. In fact, it's an extremely nice feature of P because we've also argued that Turing machines are equivalent to computer programs, let's say Java programs. So anything that a Turing machine can do, well, you can do it with a Java program, and vice versa. Any Java program, whatever it can solve, you can design a Turing machine for doing that. And Java programs and Turing machines are also polynomially equivalent. What this means is, suppose that a Java program takes time t of n. Well, there's a constant k such that the Turing machine which you design, which will be equivalent to that Java program, will take time t of n to the k. So there will be only a polynomial blow-up going from one model to another. Therefore, this class P, which is the set of all problems which we can solve in polynomial time, is invariant under all these models. The second important thing about P is that it roughly corresponds to the problems that can be solved realistically on these models. So what the class P is the set of problems that we can solve practically. What we are really trying to capture is which problems are tractable, which problems are solvable in reasonable amount of time. Time is an extremely important resource. When you run a computer program, usually you want your output to come back to you as quickly as possible. That's why we keep buying more and more expensive computers. So P is the set of all problems that we can solve in reasonable time. Actually, this definition of P was given to us by a great computer scientist named Jack Edmonds. What he did was he wrote a very famous paper in which he showed that the maximum matching in a graph could be solved in polynomial time. And at that time, he did not call this class P, but he said that his algorithm was a good algorithm. It was good because it took polynomial time. And he said that all algorithms that take super polynomial time, or all problems which take more than polynomial times, should not be considered tractable. And he, in that paper, also conjectured that the Hamiltonian cycle problem does not have a good algorithm. We will talk a lot about this aspect and about this conjecture. It's one of the most central conjectures in computer science. But let's go on and try to understand this class of problems P. When I define it to you abstractly, you do not really get a feel for what kind of problems are in P and what kind of problems you might expect not to be in P. So let's look at a few examples of problems which are in P, and you can appreciate this class a bit more. Thus, in defining P, we can talk about a single-tape Java program or multi-tape Turing machine. They all give the same definition of P. The second point is that problems in P can be solved in reasonable time. However, there's one objection. Someone can point out that if a problem can be solved in time order n to the 5000, or if somebody finds an algorithm to solve a problem in order n to the 5000, then such algorithm cannot be of practical value. This objection is very valid to a certain point. However, calling P the threshold of practical and unpractical problems has been extremely useful. There are other classes also that are used for same purpose in complexity theory. Let's now look at our first example of a problem that is in P. Suppose you are given a graph, a directed graph, which I will call a digraph, along with two nodes S and T. And what you would want to know is if there's a path that is going from S to T. So I want you to design an algorithm which will take as an input a directed graph G and two nodes S and T. And it would find out if there is a path from S to T. If there exists a path from S to T, the algorithm will accept or say yes, otherwise it will say no. So, and I want you now to design a fast algorithm, a polynomial time running algorithm, so you cannot take exponential time or more than polynomial time to solve this problem. Let's define everything formally. So path is going to be the set of all encodings of a graph and S and T such that G is a directed graph that has a path from S to T. What we want to show is that path is in P. Let us understand this question. The question exactly says, design a polynomial time algorithm that takes as an input a graph and two vertices S and T suitably encoded and decides if there is a path from S to T. So one thing we have to agree on in order to make this problem extremely well defined is how will we encode a graph and the two vertices. Well, you know how to encode graphs. You must have learned that in your algorithms course. There are two easy ways to encode a graph. One way to encode a graph is to use an adjacency matrix. Another way to encode a graph is to use an adjacency list. Actually, in our case, it doesn't really matter. You can take any one of those ways of encoding a graph, and that would be sufficient. We will show that no matter what way you encode the graph, this problem can be solved in polynomial time. How are we going to show that path is in P? We have to give a polynomial time algorithm for this problem, and the basic idea is to start a breadth first search or a depth first search from S and see if T appears in this search. If it does, then there's a path from S to T. So in your data structures courses and algorithms courses, you learn this algorithm called depth first search and another one called breadth first search. Both these algorithms can be used to solve this paths problem. Actually, in your algorithms course, you study depth first search and breadth first search quite clearly, and you analyze them. And you prove that depth first search takes linear time in terms of the number of edges in the graph, and breadth first search also takes linear time. The time taken by depth first search and breadth first search is order V plus E. So any one of these algorithms can be used to solve this problem, and that would show that this problem is in P. Since in our course we are talking about Turing machines, I will spell out the solution for you in terms of Turing machines. Let's look at this algorithm in detail. On input G, S, and T, where G is a directed graph, the first thing we will do is we will mark the vertex S. And now we will repeat this step until there are no additional nodes that are marked. We'll scan the edges of G, and if we find an edge A, B, which is going from a node A to B, and A is marked and B is unmarked, then we'll mark B. Once this loop is repeated several times, after that no additional vertices will be marked. In the end, we'll check to see if T is marked, and if it is, we'll accept, otherwise we'll reject. So the basic idea is to do breadth first search. We start with the vertex S and mark it, and then we go in through the adjacency list, and that would tell us what are all the neighbors of S. And we go and mark all the neighbors of S. And we'll continue doing this. Then in the next pass, we will go through all the edges, and we'll see if there's an edge which is from a marked vertex to an unmarked vertex, and keep marking those. After a while, this procedure will stop marking any further vertices. At that point, we'll stop and see if T is marked. If T is marked, then there's a path from S to T, otherwise there isn't one. Well, so we have just described an algorithm or a Turing machine, and you can easily see how you can implement or how you can come up with the implementation level description of this algorithm. But let's analyze this algorithm and see how much time this algorithm takes. Well, one thing to notice is to find out how many times this loop will run, this repeat loop, because we have no control over how many times it will run. The claim is it can run at most m times, where m is the number of nodes in the graph. Why is that? Because every time the repeat loop operates, it marks at least one vertex. If it doesn't, then we come out of it. And there are only m nodes in the graph, so every time at least one node gets marked, and therefore this repeat loop cannot run for more than time m times. Each time in the repeat loop, all the edges are scanned. Since the number of edges is at most n squared, thus step 2 will take time at most order m squared. So the total time taken would be order m cubed. So we have shown that path is in P. What we have shown is if you have a graph on m vertices and you use this algorithm, this Turing machine, then this algorithm will run in time order m cubed and tell you whether there is a path from S to T. Notice here that the length of the input that you give to this algorithm will be at least m. You cannot describe a graph in less than m bits. Therefore, this is a polynomial time algorithm. The running time of this algorithm is polynomial in the length of the input. Let's now look at another example of a problem which is in P. Let us say that we have two integers x and y, and we call them relatively prime if the largest integer dividing them both is 1. So two integers are relatively prime if the largest integer that divides both of them is 1. In other words, their GCD is 1. We will collect all the pairs of numbers which are relatively prime and make a language out of it. More formally, rel prime is the set of all encodings of pairs of numbers x and y such that x and y are relatively prime. The question is whether this language is in P. If we think about it, we are being asked to come up with a polynomial time algorithm which tells us whether the GCD of two numbers is 1 or not. This algorithm will take two numbers and decide whether the GCD of these two numbers is 1 or not. Now, let us first start with a bad algorithm, with a wrong solution to this problem, and see why the solution is wrong. And I'm doing this, giving you a wrong solution first in order to explain to you a subtlety. Let's look at this bad algorithm. This bad algorithm takes as input two numbers x and y. It then computes the minimum of x and y, which is not very hard to do. And now it runs a loop for I going from 2 to m. Check if I divides both x and y. If I divides both x and y, reject. On the other hand, if no I divides both x and y, then accept. So this is a straightforward algorithm. I can call it exhaustive searching. What we have is two integers x and y, and it is going from 2 to the minimum of x and y, trying to divide both the numbers x and y with this integer I. If it ever finds that something divides them both, it declares that their GCD is not 1. So the algorithm is obviously correct. Well, now let's analyze the algorithm and see how much time does it take. Well, let's just try to see how many times this loop will run. First, what we have to do is compute the size of the input. Remember that the numbers are expressed in binary. So the length of the number and the number are two different things. Let us say that x and y are both k-bit numbers, so the size of the input is going to be at least 2k or about 2k. So you can take two k-bit numbers and their size, their length is 2k. If x and y happen to be both relatively prime, then the for loop will run all the way up to x. Since x is the smallest number, the for loop will run from 2 all the way up to x. It will keep trying to trial divide these two numbers, keep failing, so the for loop will run as many times as the number x is. But what we want to do is figure out how big is x. Well, since x is a k-bit number, therefore x is at least 2 to the power k. So the number x is exponential in its size. If you write down a 30-bit number and it starts with a 1 followed by the smallest 30-bit number that you can write is 1 followed by 30 zeros, this number is not 30, this number itself is 2 to the 30. So this loop will run 2 to the k times. 2 to the k is exponential in the size of the input, which was 2k. Therefore, this is not a polynomial time algorithm. And therefore, this algorithm or this Turing machine does not show that relatively prime is in P. Let's look at this problem in more detail by the help of an example. Suppose that x, which is written for you on the screen, is the number 1 followed by 50 zeros. And let's say y is the number 1 followed by 49 zeros followed by a 1. So in this case, x is 2 to the 50. The size of the input is counted in bits would be about 100 bits. So the size of the input is 100 bits, but x is 2 to the 50. So this loop will be executed 2 to the 50 times, about 2 to the 50 times, actually 2 to the 50 minus 2 times. That is enormous amount of time. So this algorithm will fail or will take an extremely long time if you give it a 50-bit number. This is not an efficient algorithm. It's an exponential time algorithm, exponential in the size of the input. So we do not have a polynomial time algorithm yet, but you know of a polynomial time algorithm that computes the GCD. In fact, in elementary school, every one of us learns how to compute the GCD, and one of those algorithms is called Euclidean algorithm. That's an extremely ancient algorithm known to Euclid. It has been known for about 2,300 years. It's an extremely old algorithm, and it is taught to all the children in elementary school. That's called the Euclidean algorithm. The Euclidean algorithm, it turns out, is a polynomial time algorithm. Let's prove that. Once we show that it solves this problem, it can compute the GCD in polynomial time, it will be easy to show that this problem is in P. So let's review the Euclidean algorithm. This algorithm takes input x and y, where x and y are two numbers, and then it computes the remainder of dividing x with y. So r is set equal to x mod y. If the remainder is 0, which means y divides x, then the GCD of x and y is of course y. So if y divides x, then y is the largest number that divides x in itself. Therefore, the GCD is y. On the other hand, if y does not divide x, this means the remainder would be non-zero. The Euclidean algorithm then just proceeds to calculate the GCD of y and r, and it declares that to be the GCD of x and y. This is the Euclidean algorithm, and you know how it works. You've been using it in elementary school. What we want to do is now analyze this algorithm. We want to see how much time does this algorithm take in terms of the size of the input. Well, first thing what we are going to do is look at a minor point. Let's first ask ourselves what would happen if we give the Euclidean algorithm two numbers such that x is less than y. Well, if you carefully study the algorithm, you'll realize that these two numbers will be swapped, will be exchanged in the first iteration. After that, x will always be larger than y. Once x is greater than y, then it's always the case that x is greater than y in the next recursive step. That's because r is the remainder and r is always less than y. So the algorithm starts with xy and replaces that with y and r. What we need is a little theorem or a little fact that will prove about the Euclidean algorithm. The Euclidean algorithm replaces the pair xy with the pair y and r. What we will prove is that either y is less than or equal to x over 2 or r is less than or equal to x over 2. Why is this theorem important? Well, suppose x has m bits and y has t bits. So right now, the size of the input that's given to the Euclidean algorithm is m plus t bits. This shows that when we replace x and y with y and r, either we get that y has m minus 1 bits and r has at most t bits, so the total number of bits is m plus t minus 1, or y has t bits and r has at most m minus 1 bits. Thus, once again, the total number of bits between y and r is m plus t minus 1. So what we're saying is in each step, the number of bits always shrinks by at least 1. So the number of recursive calls that this algorithm will make will only be as many bits there were in x and as many bits there were in y, because it's eating away 1 bit in every recursive call. So if we prove this theorem, we will prove that the Euclidean algorithm is a polynomial time algorithm. So let's go ahead and prove this theorem. So the theorem says that if you take the pair x and y and apply one step of the Euclidean algorithm and replace it with y and r, then y is less than or equal to x over 2, or r is less than or equal to x over 2. Well, the first point is if y is less than or equal to x over 2, then we are done. So we may assume that y is greater than x over 2. In this case, what is r? Well, r is the remainder of dividing x with y. So it's going to be x minus y, which is less than x minus x over 2, because y is now greater than x over 2, and which is equal to x over 2, and we're done again. So this fact was very easy to prove, and it shows that the Euclidean algorithm is a polynomial time algorithm. Thus, relatively prime, that set that we, or language that we had made, is in P. We will also state a much more general theorem, and this theorem says that every context-free language is in P. Well, so if you have a context-free language, that language can be decided in polynomial time. In order to prove this theorem, what we will have to do is review what we had learned already about context-free languages and that you learned in your automata course. The basic idea of the algorithm is that if a language is context-free, then you have a context-free grammar that generates that language. You can take that grammar and once and for all convert it into Chomsky normal form, and from there you can use a dynamic programming algorithm to show that this problem is in P. We will not go over the details of this theorem, but this is another example, or this is infinitely many examples of problems which are in P. If a language can be described by a context-free grammar, then that language is in P. Now let's move on and define another very important class of problems which is called NP. First, let's define n time t of n to be the set of all languages that are decided by order tn time non-deterministic Turing machine n. So n time t of n is the non-deterministic analog of time t of n. Time t of n was the set of all problems that could be solved in time t of n by deterministic Turing machine, and n time t of n is the set of all problems that can be solved by non-deterministic Turing machines in time t of n. So this is just the non-deterministic analog of the deterministic class. Now NP is the non-deterministic analog of P. So formally NP is just the union over all k of n time n to the k. Or we can say that NP is n time of n, n time of n squared, union n time of n cubed, union n time of n to the 4, and so on. So NP is the class of problems or class of languages that for which we can find a polynomial time Turing machine which is non-deterministic. So all the problems that can be solved by non-deterministic Turing machines in reasonable time is what we call the class NP. Notice that non-deterministic time doesn't have any analog in real life. We cannot make non-deterministic Turing machines. It's just a mathematical definition. But this mathematical definition has proven to be extremely useful. Well, I told you about the class P and I gave you a formal definition of what this class was. But I said that in order for you to really get a feel for what this class was, you should look at some examples. And we saw two very concrete examples, path and relatively prime. So in order to understand this class NP, we should also look at some examples. But before doing that, let's look at what non-determinism is very carefully. Let's start by looking at a very simple and important non-deterministic Turing machine. This non-deterministic Turing machine has the following transition function. If it's in state Q0 and it's reading a 1, it can make two choices. It can either convert that 1 into a 0 or leave that 1 alone and move to the right. When it reaches a blank symbol, it simply halts. So imagine 1's written over its state. Now this non-deterministic Turing machine reads the first bit and it has a choice of making that into a 0 or 1. Then it moves to the next bit, it sees a 1 and it has a choice of making it a 0 or into a or leaving it alone as 1. And every time it scans the bit, it has a choice of whether to change this bit or not. When it reaches the end, it has taken the input 1 to the k and changed it. Each branch of it has changed it in a different way. If we look at all possible branches, we realize that it has converted 1 to the k into all possible strings of length k. Thus, what we can say that each branch of this is exploring one of the possibilities that a string can have. In effect, we can say that this Turing machine has guessed a value of a k-bit string. That's what non-determinism is. Non-determinism is in some sense the power of being allowed to guess something. Let's have a look at this with a computation of this Turing machine and see the computation tree and see how it looks like for k n is equal to 3. As you can see, this tree has depth 3 and it has 8 leaves. And these 8 leaves are all possible strings of length 3 that you can have. So each branch of this non-deterministic Turing machine can be thought of as exploring one possible string x of length 3. Similarly, if we give it the input 1 to the n, then it will have 2 to the n leaves in the end, and each one of those branches will be exploring one possible string of length n. We will denote this Turing machine with G, and we will call this Turing machine our guessing Turing machine. This Turing machine has the power of guessing. If we give it a string 1 to the n, it will convert that string into a string of length 01 string of length n, and it will have 2 to the n branches, and each branch will contain a distinct guess. Now let us look at an example of a problem that is in NP. Let's define composite numbers as a language. So what we want to do is we want to take integers and write them in binary and collect those integers which are composite. Formally, composite is the set of all encodings of n such that n is equal to p times q for some integers p and q which are strictly greater than 1. To show that this problem is in NP, we have to show a non-deterministic Turing machine that accepts all composite numbers given in binary and runs in polynomial time. Here is this Turing machine. So now we will describe a non-deterministic Turing machine that accepts this language and runs in polynomial time. What we will do is, in order to describe our non-deterministic Turing machine, we will call our previous non-deterministic Turing machine G as a subroutine to do some guessing for us. So on input n, we will first look at k, the number of bits which are there in n. So k is the length of this integer n. Now we will use our Turing machine G to guess a k-bit number p. Then we'll again use this Turing machine G to guess another k-bit number q. And in the end, we have a last deterministic check which will multiply p and q and check whether it is equal to n, and it will also check if p and q are greater than 1. If this is the case, it will accept, otherwise it will reject. So this Turing machine is very simple. It uses G to guess p, then it uses G to guess q, and then it multiplies p and q and sees if it gets the integer n back, and it also checks whether p and q both are greater than 1. If it ever finds such p and q, then it accepts, otherwise it rejects. So let's look at this thing in more in detail. Suppose that I give this Turing machine the input 15 in binary. When we give this Turing machine 15 in binary, when we run G, it will branch off, and each branch will guess a 4-bit number. One of these branches will guess 3, the number 3. So in this case, p is equal to 3. Similarly, when we run G again, it will branch off, and each branch will guess another number, and one of those branches will guess the number 5. And this particular branch will accept. Thus, by definition of acceptance of a non-deterministic Turing machine, 15 will be accepted. So the number 15 will be accepted because there's one branch which we follow, the one which guesses 3 and then 5. That branch will eventually make the check 3 times 5 is equal to 15, 3 is greater than 1, 5 is greater than 1, and it'll accept. And therefore, this Turing machine will accept 15. Let's see what happens if we give 13 as an input to this number. Remember that 13 is a prime number. Well, when we run the guessing Turing machine G, it will branch off, and each branch will guess a 4-bit number. So every branch will have some number p. Similarly, when we run G again, it will branch off, and each branch will guess a number, and each branch will have another number q. No branch will accept. That's because the condition 13 is equal to p times q, and p greater than 1 and q greater than 1 cannot be satisfied by p and q. Thus, 13 will be rejected by all branches, and therefore 13 is rejected by this non-deterministic Turing machine. Let's analyze this Turing machine and see what it's doing. Suppose if you give it a composite number. If you give it a composite number, by definition, a composite number can be split into two numbers, p and q, so that p times q is that number, and both p and q are greater than 1. If you give it a composite number, then there'll be at least one branch of the guessing machine which will lead to the p, and there'll be another branch of the guessing machine which will lead to a q, and that particular branch will accept. On the other hand, if you give it a number which is prime, then no matter what guess the guessing machine takes, it will always fail the last test, and therefore all prime numbers will be rejected by this Turing machine. So this Turing machine accepts exactly prime numbers. It's a non-deterministic Turing machine. So what we have shown is that this is a non-deterministic Turing machine that accepts composites. It is easy to see that the length of any branch is polynomial in the number of bits in n. Thus, this is a non-deterministic Turing machine that accepts composites in polynomial time. So, composites is in NP. What we have seen is a first example of a problem that is in NP. In the next lecture, we will look at a few more examples of problems which are in NP. You must get a feel for what this class is. We will also give a different characterization of the class NP in terms of verifier. I'll see you next time. Thank you and goodbye.